Okay, good afternoon, guys, and welcome back again to Algebra 2 Semester 2. If you're watching this video, it's because I am still not quite ready to come back to the classroom. I'm hoping that when I take another COVID test a little bit later this evening, that I'm feeling a little bit better and able to come into the room and not be sick and infecting everybody else around me. But that's yet to be determined. So at this point, I decided to record this video just in case that I was going to be gone for one more day on Wednesday the 20th. I'm hoping eventually to be able to return to the classroom and get off the sidelines here. Yeah, I would much rather be in the room working with you guys to kind of help me through the material than doing things this way. But for what it is, here is going to be our video lesson for kind of our second lesson, working through rational and reciprocal functions. In this video lesson, we're going to talk a little bit more about graphing reciprocal functions. We're going to talk about graphing with transformations. We'll do some analysis of things like domain and range, vertical versus horizontal asymptotes, and the end behavior of these guys. We're essentially just sort of building on the basics that we started developing on our first lesson around in 6.1, where we just sort of introduced these guys and talked about some of the things that they do as the inputs kind of vary between different values. What I have for you on this slide in the presentation is just the phone slot assignments for the wooden caddy there. We have one student who joined our roster, so I've added you in, Logan, on slot number 9 there. So if you haven't already, please make sure to put your phone into the correct numbered slots here. We'll go 1 through 11 for this particular list. Apart from that, though, as we get rolling on our time for today, similar to our last lesson where we were doing just a little bit of math review, just a mixture of some skills from stuff that we saw in previous years, I want to do much the same thing here and just kind of get you guys rolling some nice, easy math. Towards the back of the classroom, there should be lots of little mini whiteboards. There should be lots of rags and some dry erase markers. I want you to go grab one of those each and start trying to work through some of these expressions as you see them here on this slide in the video. Last time we were working with some fraction expressions. In particular, we were talking about how to simplify and multiply fractions. We're going to do something similar here. It's just now we're going to think about dividing fractions. So go ahead, grab the supplies that you need, pause the video, take maybe like 3, 4, 5 minutes with your group mates and try and simplify these guys down. Then unpause the video and we'll sort of pick it back up and go from there and talk a little bit more about some of the results we'll see for these guys. All right. So what we're looking at are fraction operations. In particular, the first thing you might notice is that the very first thing we're asked to do is divide the fractions. And then from there, sometimes we'll need to simplify them. So we want to probably review what it means to divide a fraction, and then we'll think about how to simplify it as we go a little further along. Now, this first example is a pretty good one. This is 9/6 divided by 6/5. And what we probably want to do is sort of conceptualize this idea of what it means to divide a fraction in the first place by another fraction. And maybe the way that I want to go about that is to start maybe with some whole numbered results. So let's say that I wanted to take 1 and I wanted to divide it by 2. Well, if I take, say, one complete object and I divide it into 2 groups, in each of those groups, I'm going to have half of the original object, right? So we could say that 1 divided by 2 is a half, or it's equal to something like 0.5. But what I did in that instance, right, is I just took that thing and I split it into 2 smaller but equally sized portions. When you think about something like 1 divided by 2 becoming a half, one thing that you could think about here is that that's sort of the same thing as doing 1 times a half. So it's kind of just like having something, and you get the same result by thinking of it that way. Now, the reason I wanted to point this out, because this seems kind of silly, right? It just sounds like I'm just sort of playing with words and phrasing here, is that division by 2 was equivalent to multiplying by 1 over 2. And in this case, if you think about just 2, you could have written that as the fraction 2 over 1 without really hurting anything. So if you're thinking about, say, fractions divided by fractions, so if I did, say, 2/3 divided by a half, that's a pretty weird thing to conceptualize. if I had, say, a whole object and I had 2/3 of that I was trying to divide into half groups. So not two whole groups, but half groups. That's a really weird thing to draw or try and conceptualize, right? But if you think about division by something as being like multiplying by its flipped version, so it's reciprocal, we say in math, it's a little easier to think about. And that comes back to what we saw in our last lesson, where I could say, hey, 2/3 of 2 is going to be something like 4/3. I can multiply the numerators and the denominators together. And if I wanted to think about it, say, in like kind of a picture format, so if I had, say, two whole objects and I broke them down into thirds and I took 2/3 of each one of them, I would see that I'd have like 4/3 of the original object. So I get the same answer either way, right? That approach is going to probably prove pretty useful here when you're trying to divide fractions. So if I take 9/6 of something and I'm trying to divide it up into like 1.2 groups, I'm trying to divide it up into 6/5 groups. That's a weird thing to think about, but it might be a little easier instead to say, okay, well, that's just kind of like 9/6 times 5/6. And as soon as I switch over to multiplication again, then I can do 9 times 5 is 45 in the numerator, and I can do 6 times 6 is 36 in that denominator, and then I can start to simplify my fraction down from there. Now, one way to simplify fractions is going to be to say, let's focus on the numerator and the denominator separately. Let's find some factor pairs, and we want to find the largest common factor that they have. So we can sort of divide it out of both of them and reduce down the values involved in the fraction, right? 45 is like 1 by 45. It could be written as 3 by 15. It could be written as 5 times 9. 4 doesn't divide nicely into 45. 6 doesn't divide nicely. 7 doesn't divide nicely. 8 doesn't divide nicely. So those are probably all the factor pairs. If I think about 36, it's a little more highly divisible. I could do 2 times 18 is 36. I could do 3 times 12 is 36. I could do 4 times 9 is 36. 5 doesn't divide nicely into it. I could also do 6 times 6. But if you look at their common factors, they both have a factor of 9 in common, and that's the largest one that they can share. So what I can do here is write 45 as 5 times 9, and I can write 36 as 4 times 9, and then I can cancel the 9 divided by 9, and I get my answer there of just 5/4. So the final simplified version of my answer there for 9/6 divided by 6/5 would be 5/4. It's going to be much the same when we tackle these two guys kind of in the middle and on the right. One thing that you may have noticed here is that instead of just numbers, you've also got some variable expressions. And in that guy on the right-hand side, you have variable expressions with exponents. So we're kind of like dovetailing all the simplification review that we did in the first lesson and some of the examples that we see here. Now, same thing, thinking of division of a fraction is kind of a strange beast. So I'm going to switch that over. Instead of thinking about division by a fraction, I'm going to switch it to multiplication, but I'm going to flip the numerator and the denominator of my second fraction. I'm going to think about the reciprocal in this case. That's a much easier thing to sort of visualize. Now, if I'm thinking about this, what I could say is like 9 times 8, well, that's 72. 5 times 4 is 20. 20 times x is 20x. So I've got 72 over 20. And then I could sort of play this game of finding the factors of 72 and the factors of 20 and finding the greatest common factor that they have in common. But some of you guys may recognize that you don't necessarily have to do that simplifying right at the very end. You could actually kind of do it right in the middle of the process. And here's what I mean by that. If you take a look at 8 and 4, they're on opposite sides of the fraction. The 8's in the numerator of the fraction on the left, and the 4's in the denominator of the fraction on the right. Now, 4 divides nicely into itself, and it also divides nicely into 8. 4 divides nicely into itself one time, and it divides nicely into the 8 two times. So you could do the simplification at the end where you kind of approach it with that greatest common factor strategy. Or maybe a different thing that you do is you say, well, wait a minute, what if I do it first, and then I can do this as 9 times 2 is 18, 5 times 1x is 5x, and then we're just sort of done there, right? So there's sometimes a more efficient way to simplify that fraction down. I could write this as 18 over 5x, and then I'm good to go. So you don't always have to do it just one way. I wanted to kind of highlight that there. Now, very similar for this guy on the right-hand side. 3 over 7x to the third, that's my first fraction. If I'm dividing fractions, I like to switch over to multiplying by the reciprocals here. So I'm going to switch 4x to the third to being in the numerator of the second fraction. I'm going to switch 7x to the squared, being on the bottom of that second fraction there. And then I'm doing the same game, right? I'm saying, okay, is there any simplification that I can do before I multiply the numerator of the numerator and the denominator of the denominator? 3 divided by 7. 3's not going to go into 7 nicely. 7's not going to go into 3 nicely, so there's really no simplifying there. 4 and 7 in that second fraction. 4 doesn't go into 7, and 7 doesn't go into 4, so that's kind of done. But if you think about the variable terms here, notice that you have x to the third eventually going to be divided by itself. And if you take something divided by itself, it just sort of cancels out and it leaves behind a 1, right? We call that the multiplicative identity in algebra. So I could recognize that there's going to be that simplification there. So in the numerator, I've just got 4 times 3, which is 12. Here in the denominator, I'm going to have 7 times 7, which is 49, and then times x to the second. And then it might be worth trying to check, right? Am I going to get any sort of simplifying that's going to happen in this case? Well, if I take a look at 49, it could be 1 times 49 as a factor pair. It could be 7 by 7. None of those are factors other than 1 that are also going to be factors of 12. So that's about as simple as that fraction is going to get. There's not much else that we can do to simplify that guy down. So just a little more review, right? And as we go, I think I'll kind of work these in. We'll get some practice with these just to kind of freshen up the skills from what we saw last year, especially because they're going to become more and more relevant as we get a little bit further in the unit on rationals. Rationals and reciprocal functions involve fractions, of course, so we're going to see lots of that as time goes on. Now, the other thing that we're going to talk a little bit more about is some factoring review. We're going to have a whole day set aside to practice factoring in a variety of different contexts and strategies, but I wanted to sort of front load some of that with our next 2 slides where we're going to take 4 expressions and we're going to try and factor each of them. Now, in our last lesson, we kind of talked about a flow that we work through when we check for factoring. I want you to try and think with your group mates. What is that flow? What's like the procedure, the process that we go through? And given the type of polynomial expression that you're working with, what is the correct factoring strategy to try and implement to factor it down completely? And go ahead and try and do this with your group mates. Maybe these two here. You've got x squared minus 3x minus 12 and 4x to the third minus 16x. Pause the video and go ahead and try that for maybe like 3 to 5 minutes. So what I'm going to notice, as far as like factoring is concerned, right, is that if I take a look at my very first expression that I'm trying to factor, that thing's got 3 terms, which means it's also known as a trinomial. Tri meaning that it has 3, and nomial means that it has terms in this, 3 terms in that case. If I take a look at this example on the right, I see that it has 2 terms. So I might say that that's a binomial, bi meaning 2 in this case, right? And if I know the number of terms that I'm dealing with, that's usually going to help me figure out what I'm going to want to do as far as my factoring strategies are concerned. And what we saw in the last video is that there's always something we check for before we kind of move in the rest of the process, right? There's always this notion of, is there a GCF? So I check for GCFs before I make decisions, but the decision that I make as far as factoring strategies has to do with the number of terms that I see. So if I have 2 terms, that's going to be a difference of perfect squares that I want to check for. If I have 3 terms, that's going to be the AC method that I want to check for. And if I have 4 terms, this is where we refer to it as factor by grouping, right? And we'll see an example of that on the next batch of problems that we work real quick. So there's ultimately 3 primary factoring strategies. The one that we apply depends on the number of terms that we're working with. the one thing that we always want to check for is a GCF. So if I'm taking a look at, say, this example on the right-hand side of the board, I've got two terms, so I'm probably going to want to try and hit it with a difference of perfect squares. But I also want you to notice that there's a GCF at play. If you're taking a look at the constants of 4 and 16, they have a greatest common factor of 4 that I can factor out of both of them. And if you take a look at, say, the variable terms, where I've got x to the third and then just x, I could factor out an x from both of those. So my GCF in this case is 4x. Now, in order to figure out what goes inside the parentheses, I have to sort of work backwards here to say, what do I multiply by 4x to get back to 4x to the third? And that first term is just going to be x to the second. 4 times 1 goes back to 4, and x times x squared goes back to x to the third. The rightmost term, if I do 4 times 4, that would get me back to 16, but then I don't really need a variable there, right? Because 4x times 4 would get me that 16, and then the x is back. So inside parentheses, I've just got that x squared minus 4. Now, this thing left over inside parentheses, this x squared minus 4, what I want you to notice is that that thing's still got two terms. It's still a binomial. So I want to try and factor that using the difference of perfect squares. And when we talked about the difference of perfect squares in our last lesson, we kind of highlighted the fact that this is like x to the second plus 0x minus 4. There's that missing b term when we write it in standard form, right? So if you're doing this kind of the long way, where you're doing an AC method on this guy, what we're going to do is we're going to find the factor pairs of, say, -4 that add or subtract somehow to completely cancel each other out and be nothing. And that's where you see that you need a -2 and a +2. So ultimately, this guy's going to factor. It's going to have that 4x on the outside, but then you're going to have two factors on the inside of that larger set of parentheses, where one's x minus 2 and one's x plus 2. The other thing that you might notice is that if it's a difference of perfect squares, then 2 by 2 is 4, and x by x is x to the second. So you just write x2, x2, and you switch the signs between them. Just kind of a faster way to do that, right? There's a shortcut. Now, this guy over here on the left-hand side of the board, this is something with 3 terms. So I want to probably factor it using the AC method, which is also known as the X method. I'm not seeing a GCF, though. The A term in this case is a 1. The B term is a -3, and the C term is a -12. They don't have a factor in common other than just 1. So there's really not much I can do there. So what I'm going to do next is I'm going to say, okay, A times C, that's -12. I need to find the numbers that multiply to -12, but give me a B term in this case of -3. So that when I add or subtract them together somehow, the difference is 3 in the negative direction. If I think about the factors of 12, it could be 1 and 12, it could be 2 and 6, it could be 3 and 4. If I take a look at some of these values, I want to find the one that's going to give me a difference of 3. And if I'm taking a look at this in this particular instance, ooh, I think I made a boo-boo. I think this guy might be a bit of a problem in the sense that I think I wrote down the wrong number here. I think this -3 needs to be a -4 there. Yeah, I think I made a typo there on that one. So we'll switch that to being a -4x minus 12 there, and I think that will work a lot better. You'll notice here that in the factor pairs, that 2 and 6 can have a difference between them of 4. If I want, say, the difference between them to be -4, I could do -6 and +2, and when I add those together, the difference is -4. When I multiply them together, I get -12. So then I can finally say, okay, this guy's going to factor into x minus 6 and x plus 2. And we're fine on that front, right? We've got that guy factored out. Now, I'm taking a shortcut here for AC method problems. In the last 2 lessons that I've done, you'll notice that the A term was just a 1. In those types of scenarios, it's sort of the simpler version of the AC method, and we'll kind of revisit the more challenging version as we get a little bit closer, maybe to lesson 6.3. But what I really want to do is just kind of knock the rust off of the basic approaches, the basic strategies. Here's maybe the last factoring one. I want you to pause the video with your group mates here and maybe try these for a few minutes. You'll notice that this guy on the left has 4 terms, so maybe a different kind of approach that we'll take there with factor by grouping. This guy on the right, still 3 terms, so probably an AC method problem. Go ahead and run these real quick. Pause the video, and when you're ready, come on back in about a few minutes or so, and we'll pull it together. So this guy on the left-hand side, you'll notice that this one has 4 terms present. And once it's more than 3 terms, we usually just refer to it as a polynomial, where poly means many in that context. The A term is a 1, the B term's like a -2, that C term's like a 3, and that D term now, that constant, that's like a -6. If I'm thinking about factor by grouping, as far as my factoring strategy is concerned, factor by grouping is kind of nice in the sense that you're pairing off terms in this 4-term polynomial, and you're essentially hunting down some GCFs. So what I mean by that is if you're focusing on the first 2 terms, where it's x to the third and -2x squared, you'll notice that the constants front don't really have a factor in common other than a 1. But if you think about x to the third and x to the second, they have an x to the second in common that you can factor out of both of them. So inside parentheses, what I'm thinking about are the missing terms that I'd multiply by x squared to get back to the original 2. So the first one will need to just be 1x, and the next one will just need to be -2, right? And I can leave that as just x minus 2 there. And then that guy's good to go. Factor by grouping works the same way with the second pair. I want to try and find a GCF of both of those terms. And what you'll notice is that this strategy succeeds when the things in parentheses are exactly the same. If I look at 3x minus 6, I can factor a 3 off of both of those. And if I don't specify, I'm going to assume that that's a positive 3. It's going to leave behind something and something so that when I multiply by 3, I go back to being 3x and minus 6. So in the first term, I'm going to need an x. In the second term, I'm going to need this to be a -2. That's the same exact thing I got in parentheses on the first go. Now, factor by grouping wraps up by saying the things in parentheses are going to form one factor, and the things that are outside of parentheses, they're going to form the remaining factor. So one of my factors is going to be x squared and then plus 3. The other factor is going to remain x minus 2. And then we have a fully factored problem from what we started with. So factor by grouping is essentially like an application of GCS. The things on the outside go together once you have them. The things that are in parentheses are going to stay that way together to form the other factor, and you're good to go. If I take a look at this guy on the right-hand side, that's 3 terms. So that's a trinomial, which means I probably want the AC method, but you may have noticed that for 3, 3, and 36, they've got a GCF in common. So if I factor out that 3 first, inside parentheses, I might be left with something that's just a little bit easier to work with. So what I might see here is that if I take 3 out of 30, that'd be like 10. So this is like minus 12 there. There we go. That bit in parentheses is what I'm going to factor with the AC method. And I'm going to be done with my problem once I get that guy factored and I just tack the 3 onto the front. So I'm going to look for the factor pairs that multiply to -12, but they add or subtract somehow to get a positive 1. The factor pairs of 12 are 1 and 12, 2 and 6, or 3 and 4. I'm probably going to need a 3 and a 4 because they have a difference of 1 between them, but I probably want the 4 to be positive and the 3 to be negative. When they multiply, they go back to being -12, but when they add, they give me that +1. So my final answer for this guy is going to be 3 times x minus 3 and 3 times x plus 4. And then I'm good to go. So just a little mixed review, right? Just a little mixed practice with some of these factoring skills. We'll have a whole lesson that we dedicate to just working on this skill in particular. It's going to show up a lot later on in the rationals unit when we talk more about adding and subtracting rational expressions. We talk about simplifying those guys. So it's nice to kind of front load it and just get the gears turning there. But like I said, we'll review a lot more of this as time goes on. For our final warm-up for today, this is getting more back into what we saw with lesson 6.1, where we're doing like an intro to rational functions. I want you to complete the table of values for the function 1 over x. And then once you have those coordinates, I want you to try and graph it, maybe on like a scratch piece of paper here, on this guy to the right. So I want you to evaluate the function for each of these inputs. I want you to notice something that's going to begin to emerge here in the pattern of behavior. So if you've got a whiteboard, by all means, feel free to go for it and just kind of work out the calculations. If you flip over the whiteboard, you'll find that you've got like a little axis coordinate system that you can use to draw a graph for this. Go ahead and try that real quick so we can kind of review what the parent function 1 over x looks like. And we'll start talking about what transformations of that are going to look like a little later in the lesson. So our function, f of x, is going to be this guy, 1 divided by x. And what you'll notice here is that in this table of values, we have a bunch of values for x given to us, and we're doing 1 divided by that to try and get an output that we're going to use to go on the graph. We've got a bunch of values to test, like 1 divided by -10, which is like -1/10 or 0.10 in the negative direction. I could do 1 over -5th, and that's -1/5, or -0.2 in that case. But I've also got things like -2 here, so I could do -1 over -2, or I'm sorry, 1 over -2 there and get -0.5. -1 in that input is going to be like 1 over -1, which is just -1. But then they sort of switch gears, right? You'll see sort of the reciprocals on the other side of -1 here. So 1 divided by -1/2. Ooh, there's that copy dot flop again, right, from our warm-up. -1, or rather +1, divided by -1/2 is like 1 or times -2. So that's like -2 now. And 1 divided by -1/5 is like 1 times -5, so that's like -5. And then you'll notice kind of a pattern here, right? 1 divided by -1/10 is going to be like -10. So the larger the input is in the negative direction, the smaller the output is. But sort of similarly here, right? The smaller the input is in the negative direction, the closer we are to the y-axis, the larger the outputs are in the negative direction. And I'm on the wrong side of the axis here. I got to sort of put these below. Whoops. Let's fix that. So that's like barely below the x-axis there. -5 is kind of like barely below the x-axis there. -1/2, little below there, -1. And then notice here, right? -1/2 jumps to -2. -1/5, so barely to the left of the y-axis, jumps to -5. And then I've got -1/10 there, which jumps all the way down to -10. So that's kind of the first half of our graph here for this reciprocal function, right? The closer I get to x equals 0, the larger the values are in either the positive or the negative direction. And you'll see much the same thing here when I test the positive input. So when x equals 1/10 and I do 1 over 1/10, I'm going to get something like +10. If I do 1 over 1/5, I get +5. If I do 1 over 1/2, I get +2. If I do 1 over 1, that's 1. 1 over 2 is 1/2 or 0.5. 1 over 5 is 1/5 or 0.2. 1 over 1/10 is 1/10 or 0.1. So as I sort of complete these tables of values, right, the main reason I wanted to review this is just so we kind of recapped and reviewed the shape of this particular graph and some interesting things about its pattern of behavior that we were working with in the first round of our notes. One thing that we noticed is that there's kind of these boundaries, right? That the graph that I drew in red here is not going to cross. It's not going to cross the y-axis, and it's also not going to cross the x-axis. And what I want you to think about real quick, maybe with your group mates, is why that's the case. If I'm not crossing the y-axis, think about this coordinate at x equals 0. What's the one number in math we don't know how to divide by? We don't know how to divide by nothing, right? And you'll notice in the table of values that sometimes I was getting pretty close to 0 for x, but I wasn't 0. So if I tried to divide by 0, I get an undefined result in the calculator, and it's got that vertical asymptote, right? That's the y-axis. There's a vertical asymptote there at x equals 0. So my domain is from negative infinity up to 0, but then from 0 out to infinity, and I can't be x equals nothing. If you take a look at some of the corresponding y values, you'll notice something similar. The y's can be really big and negative. They can be really big and positive. They can be really small and negative, and they can be really small and positive, but the y values can't be nothing. So I'm never crossing the x-axis, which is the same thing as y equals 0, and that's what we refer to as the horizontal asymptote. And that has to do with the fact that 1 divided by something is always something, even if it's really small. It's never equal to nothing. So we're just kind of reviewing, right? That there's a pattern of behavior here. Some of these coordinates here are kind of useful to use maybe as anchor points as we go along. There's a sort of general shape to this reciprocal function. And there's some interesting behavior as far as the inputs and the outputs. We have some excluded values there that we're going to explore a little more as time goes on. So moving into our lesson for today, we are going to continue to work with this reciprocal function, 1 over x, but we're also going to introduce some transformations to it. And we've talked about geometric transformations of functions in Algebra 2 in a variety of different families of functions, but for Unit 6, what we're going to focus on is just transformations in the context of these reciprocal functions. We're going to start small and kind of focus on just one transformation at a time, perhaps, but then we're going to slowly start to chain these things together as time goes on and explore some more sophisticated behavior. So reciprocal functions are, generally speaking, a family of functions in which you have a constant divided by a variable. And that constant is usually what we call the constant of variation. The graph that you see here is for what we call the parent function, which is just 1 divided by a variable instead of any number divided by a variable. It's a parent function because it captures the basic pattern of behavior that all reciprocal functions are going to have, regardless of what that constant is. So if you change it, you'll still see something similar to this guy. It's just that this is the simplest version of the reciprocal function you could work with. Reciprocal functions are a kind of rational function. It's just that they're a little simpler in the sense that the numerator is a constant instead of a variable expression. We've also previously discussed that because of the fact that the x can't equal 0 and the y can't equal 0, it's a function that has restrictions in the domain and the range. This is what we refer to as interval notation. This interval for the domain, say, of negative infinity up to 0, where you see this parentheses, means that that's exclusive of those values on the left and the right. You can never quite reach infinity because it's more of a process than it is necessarily a destination. You also can't be 0 because if you were x equals 0, 1 divided by 0 would go undefined. You'll see something similar in the range. They're saying that pretty much every y value you can think of is going to be reached by this function except y equals 0. So if y equals 0 is excluded, they're using parentheses there. And that's ultimately where those asymptotes come into play. The vertical asymptote is when x equals 0, it's the y-axis. The horizontal asymptote is when y equals 0, it's the x-axis in that particular instance. Now, the last thing that we talked about was sort of end behavior. What you probably noticed in the table of values is that as x gets really big, in the positive direction, 1 divided by a really big number gets really tiny. And the same thing happens in the negative direction, right? 1 divided by a really big negative number is a really tiny negative output. So as x goes way out to the edges, as it goes out to the left towards negative infinity, or as it goes out to the right towards positive infinity, the outputs for f of x are approaching 0. They'll never quite reach 0, but they're approaching it. And when we talk about end behavior, we usually use this sort of limit notation to discuss it. Now, as we go into our activity for today, the sub should have some copies of what are going to be the notes today for 6.2. They should also have, for you guys, a few extra copies of a practice for 6.2. The practice for 6.2 is going to be a matching activity. And I've made a digital version of that you're going to find on Schoology. But if for some reason you're unable to access it, the sub should have extras of those as well. So go ahead and make sure that you get a copy of the notes today from the sub in 6.2. What we're going to start to explore here are graphs of reciprocal functions where there may or may not be some transformations present. In our last lesson, we were working with 1 over x. And before we start talking about related functions with transformations, we want to continue to sort of work our way through analysis of these guys. So if I've got 1 over x here, you'll notice that I don't have like a table of values. I've only really got just a couple of coordinates. And I haven't really drawn very much on here. What I want you to do real quick is recognize where are your asymptotes and what are some of your anchor points, right? So you'll notice these sort of half filled in coordinates. Go ahead and fill in the missing y values there, and go ahead and jot down where you believe the asymptotes are. So as we take a look at this activity, we'll notice here for the anchor points, right, that there's an incomplete set of coordinates. There's 1 comma blank and -1 comma blank. When I talk about a coordinate notation, it's a set of ordered pairs where it always goes in the order x versus y, input versus output. So here, when they say x equals 1 and the y value is missing, I'm trying to figure that out. So I go to when x equals 1 and I read off the corresponding output, which in this case is also 1. You'll see something pretty similar here for this other coordinate on the graph. This guy's here when x equals -1, but the corresponding y value is also -1. When x equals a half, what you'll notice is that the y value's close to 2. And when x equals -a half, the y value is close to being -2. So there's this sort of like opposite relationship at play with the coordinates. When x equals 2, my y value is about a half. And when x equals -2, my y value is about -a half. Now, I haven't really drawn them on the graph, but what you'll notice is that this graph is still essentially avoiding the y and the x-axis. If I'm avoiding the y-axis, which runs vertically, that's like it's passing through the coordinate x equals 0. So that's the domain restriction, right? That's that input that's not allowed to happen. The horizontal asymptote, which runs from left to right, is the x-axis for this graph, and that happens as it passes through the coordinate y equals 0. So this is just, again, a little more review, a little more repetition of the fact that it's like kind of the opposite value for vertical and horizontal. Horizontal is a y value, which we usually think is running up and down. The vertical asymptote happens when x equals 0, which we usually think of the x values as running from left to right. So it's kind of tricky there. We're just sort of hitting that one more time. As we go on our activity here, what you're going to notice is that in the notes, there's lots of graphs that we're trying to discuss. Some of them are different than what we've been seeing for 1 over just x. So what I want you to think about real quickly with your group mates is if you look at this guy, maybe where are some of your anchor points and how is it different than what we saw in the last graph? And then once you identify where some of the important things are for this graph, like the asymptotes and the anchor points, go ahead and try and figure out the domain and the range. And then maybe the last step that I want you to take here is to go ahead and try and figure out the equation for this guy. So if 1 over x is what we had before, how is this one different? And what might we write as an equation there? So one thing that I'm going to do as I'm opening up my activity here for today is just sort of think about the basics of the graph first. Where are some of my coordinates? Where do I notice my asymptotes have gone? And how is that different than what we saw in the past? What you'll notice here, if you take a look at, say, these two filled in coordinates, is that instead of being at 1, 1 and -1, -1, they're a little higher than where they should be, right? I have a coordinate here for when x equals 1 and y equals 6, and I've got this other one here when x equals -1, y equals 4. Those have traveled up from where they used to be. And in particular, if I think about what used to be at 1, 1, it's now at 1, 6, so it's gone up 5 units. And similarly, this coordinate that used to be at -1, -1 has gone up 5 units to be here at -1, +4. So the whole graph has translated in this case. It has shifted up 5 units. And what you'll notice is that this horizontal asymptote has also shifted up 5 units from where it used to be on the x-axis. Now, If the x-axis was the line y equals 0, and I go up 5 units, what you'll notice here is that this guy's at y equals 5. So I can just start to jot some of this down, where the horizontal asymptotes at y equals 5. My domain and my range are going to be kind of interesting to think about. Eventually, I'm going to want to think about how to write my old equation to get this new guy, right? To capture that pattern of behavior. Now, another thing that you might have noticed here is that this graph is still avoiding touching the y-axis. So the vertical asymptote here hasn't really changed. If you think about where these asymptotes are and where these x and y values are that I can't cross, that's where we're going to be able to start to fill out our domain and our range a little bit easier. So if my vertical asymptote is still at x equals 0, my domain is everything but 0. So it can go from negative infinity to 0, and it can go from 0 to positive infinity. It just can't include x equals nothing. The range will be a little different though. I notice that I'm hitting all the y values except 5. So I could go from negative infinity in the y values up to 5, and then I could go from 5 up to positive infinity. So everything is pretty much the same except the fact that it's gone up 5 units, and that changes both the horizontal asymptote and the range. Now, back in Algebra 2, you guys often discussed across a variety of different families of functions something called a geometric transformation. And what we're going to be working with here as far as geometric transformations are going to be something of the form like y equals a over x minus h plus k. The geometric transformations are numbers, and they show up in either the a, the h, or the k place. If I wanted to shift my whole graph up 5 units, compared to the old coordinates that I had, I still need to do the 1 divided by the x term. The pattern really hasn't shifted, but what I'll notice is that if I just plug a plus 5 onto the end of this particular equation, that's how I got that shift to go that way. That's how I got this transformation to occur. Now, I think what I'm going to do is maybe pause the video here and kind of give you some access to a useful tool to sort of review and recap these geometric transformations as we're moving through the context of our activity today. So I'm going to pause the video real quick, rearrange my slide deck, and make sure that you guys have a link to this particular demo just to help write the equations maybe just a little more efficiently. All right, so what we saw in that last example was that we had a graph that was similar to the last one we saw for 1 over x. The only difference is that just the whole thing was shifted up 5 units to be higher than where it should have been, right? And that's one kind of geometric transformation that we're reviewing in our lesson today. I decided that I wanted to rearrange my slideshow a little bit, just to put this a little earlier than where it was. What we saw back in Algebra 2 across a variety of families of functions is that there's a common set of transformations that we refer to as like A, H, and K transformations. This template here is going to work for any reciprocal function that you can think of. If you see an A term, an H term, and a K term, they're going to do unique things depending on their value and where you see the transformations happening on the graph. So the goal here for this activity, as we move into the next kind of phase of the lesson, is going to be to take some time to work independently with your group mates and try and identify how is the graph different and how is that going to be reflected in this transformation template. Now, if you go to our Schoology page, you'll notice that there's a link for a Desmos demo. If you click on that link, which I have hyperlinked in our class slides as well, it'll take you to something where you can kind of adjust and play with some of these different sliders, and it might help you visualize how these transformations are taking place to get from, say, the parent function, which is just 1 over x shown in blue, to the red function, which is going to be the transform function you're working with in your particular phase of the activity. So it's there for you to serve as a resource. By all means, feel free to use it. What I want you to do is to take some time with your group mates and work your way through as many of these graphs as you can. So you'll notice that some of these graphs are going to look really similar to just 1 over x, and some of them might start to look more and more and more different. I want you guys to think about, what do you notice is different about the graph? how does that affect, say, the asymptotes, and then how does that affect the domain and the range? But then maybe from there, how can you use those changes to write an equation that goes back to what we saw with 1 over x, but also captures the new patterns of behavior? So I'm going to walk it back to kind of the first one here in the list. I want you and your group mates to try and graph as many of these as you can. The goal here is to take maybe like 20 to 30 minutes with your group mates and try and work on it on your own. Depending on how much time you have left in class, take as much time as you need, but still leave maybe about 15 minutes here before class ends to sort of unpause the video and follow along as we work through some of these examples. So I'll turn it over to you guys, but when you're ready, come back to the video and we'll work through some of these together. So as we sort of recap what we're seeing as far as transformations are concerned, we know that there's what we refer to as a parent function, 1 over x, and we know for that parent function that usually there's a pair of anchor points, right, at 1 comma 1 and -1 comma -1. You could also go as far as saying that there's one at 2 comma a half, -2 comma -a half. There's also 1 at a half comma 2 and -a half comma -2. What you might notice about this first example is that the anchor points for 1, 1 and -1, -1 are sort of upside down. The coordinate that was at 1, 1 is now at 1 comma -1. And the coordinate that was at -1 comma -1 is now at -1 comma +1. So it's flipped itself over the x-axis. Now, it still appears that the vertical asymptote is the y-axis, which is also represented as x equals 0. And it appears that the horizontal asymptote is still the x-axis, which is represented by this line y equals 0. So if I think about the domain and the range, nothing's changed at all from our parent function, so much as I've just turned the graph upside down. So I haven't shifted it left or right or up or down. I just want to flip it. And if I'm thinking about our sort of transformation template, where I've got x minus h plus k, and I've got that a in the numerator, that means I've done something to the value of a to get that transformation to occur. Now, what you'll see if you're exploring that Desmos link is that if you take a from +1 to -1, you take that graph of 1 over x and you flip it upside down. So the only difference from our parent function is that I've taken that a from 1 to -1, and it causes that vertical reflection over the x-axis. That's how we refer to it. Now, if you move on to the next one of the bunch, what you might notice here is that the vertical asymptote is not on the y-axis anymore. It's at this line x equals 2. It's gone right 2 units. And similarly, if you compare this to, say, the parent function, which I'll draw in blue, of 1 over x, which has an anchor point at 1, 1, and another one at -1 comma -1, those have shifted right 2 units as well. So I haven't gone up or down. It still looks like my horizontal asymptote is y equals 0, but I have shifted right 2 units, so my vertical asymptote is x equals 2. My range then is going to be the same as the parent functions, from -infinity to 0, and then from 0 to infinity, but the domain's different. I can be everything except x equals 2. And if I'm thinking about my equation, and I wanted to relate it somehow to like 1 over x, I haven't gone up or down at all, so I don't have a k term that I'm adding on or subtracting. I'm not upside down, so my a value is not negative. I also haven't gone up or down any faster or slower than usual, so my a term in this case is still going to be a 1. That means if I'm shifting right, that I've done something to my h term. And this one's kind of tricky in the sense that I might initially think that if I'm shifting right 2 units, I'd write it as kind of like x plus 2 here. That's actually not quite it. It's close, but it's not perfect. Now, I'm going to switch over to my Desmos activity real quick just to show you what this is going to represent. If I take a look at some of my sliders, right, where I've got A, H, and K, and I write, say, h equals 2, that definitely shifted the graph in red to the right 2 compared to the graph in blue. But if I look at my transformation template here on the left-hand side, if h is 2, this would look like x minus 2, and it goes right 2 units. If I let h be negative 2, which would shift my graph left 2 units, x minus negative 2 would look like I was doing x plus 2, which is actually left instead of right 2 units. So you'll notice here that if we make use of that template, shifting left or right is going to be the opposite of what it appears to be. So if I want this guy to shift right 2 units, and I'm writing an equation for it, I'm going to have to make it look like it's going left. I'm going to have to write x minus 2 to get that to occur properly. And that one always gets students. That one's kind of tricky compared to what we've seen in the past. Now, let's maybe try this guy. What you'll notice here for this reciprocal function is that there's maybe multiple shifts that have happened. I have a vertical asymptote that's no longer on the y-axis. It looks like it's more like x equals negative 1. And my horizontal asymptote is no longer on the x-axis. It's gone down 4 units to y equals negative 4. So as I'm writing some of these guys down, right, that's going to allow me to make a determination about how my domain and my range is different. My domain is everything except x equals negative 1, and my range is everything except negative 4. But I'm eventually going to have to try and capture those two transformations at the same time in my equation. So if I'm thinking about my transformations that could occur, right? And this is where I'm going to come back to my idea of like my anchor points for 1 over x, just to make sure that there's not like an a transformation hiding. If I look at just 1 divided by x, I have an anchor point at 1, 1, and another one at negative 1 comma negative 1, right? This guy at 1, 1 has gone down 4 and then left 1 unit. Same thing for negative 1 comma negative 1. It's gone down 4 and then left 1 unit. It's not upside down. It's not like twice as high or half as high as it's supposed to be. So in this instance, I know my a term is just 1. It's no different than usual. But if I want my graph to go down 4 units, I'm going to have to replace k with a minus 4. And you'll see that in the Desmos activity if you're sort of playing with the sliders there. If I want to go left 1 unit, here's where I got to be careful. I've got to write it inside my equation to look like the opposite is happening. So as I put all this together, I might write x plus 1 in that denominator and then a minus 4 on the outside, and that's going to be my equation. Now, again, I'm going to sort of jump out of my slide deck here and back into Desmos just so we can sort of highlight that and make sure that that makes sense, right? If I adjust h and k to be 0 and a to be 1, I've got just 1 over x. But if I set k to be negative 4, the whole graph shifts down 4 units to be where I need it to be. And then if I want to go left 1 unit, I'm going to let h be negative 1 so that x minus negative 1 is going to look like I'm doing x plus 4, or x plus 1 rather. So my equation's correct. It's also captured the right types of transformations. My anchor points have gone down 4 and left 1, but there's no change in the pattern. They're not right side up versus upside down, and they're not moving any number of times faster than usual. So we'll keep playing. We'll continue with, say, this graph. Now, this is where we put kind of a lot of them together at once. Here, I'm going to notice that my vertical asymptote is at x equals 5. It's going to right 5 units from where it wants to be. My horizontal asymptote is at y equals 2. It's 2 units higher than it's supposed to be. So that lets me figure out my domain and range. It's everything from, say, negative infinity up to 5, and then from 5 up to infinity for the domain. My horizontal asymptote, or my range, it's from negative infinity up to 2, and then from 2 up to infinity. For my equation, I'm definitely going to see that I shifted right 5 units and up 2, but I also want to compare where these anchor points are and whether or not they're moving any faster than usual or whether they're upside down. So normally for y equals 1 over x, I have an anchor point at 1, 1, If I take this guy right 5 units and then up 2, he would have been here at 6 comma 3. But notice he's not really at 6 comma 3 for my graph in red. He's at 6 comma 5. And if you think about that in terms of the horizontal asymptote distance, that's 3 times higher than he's supposed to be. If you think about this anchor point here at -1 comma -1, and I go right 5 units and then down 2, he would have been here. I'm sorry, yeah, right 5 units and then up 2. That's where I want to be. There we go. He would have been here at 4 comma 1. But this final coordinate for my graph in red is at 4 comma -1. It's down 3 times further than it's supposed to be from the horizontal asymptote. So if I'm writing my equation and I'm thinking about like my up, down, left, and right transformations, I've definitely gone up 2 units. So I'm going to write a +2 there on the end of my function. I've gone right 5 units, so I'm going to replace h with 5, and I want it to look like the opposite, so I'm going to do x minus 5. But my pattern for my anchor points is up 3 times higher than usual. So we call that a vertical stretch by a factor of 3. That a term in this case is a 3 instead of a 1. It's moving 3 times faster than it's supposed to be. So I did all 3 transformations at the same time there. If I had noticed that my graph was upside down, then I could have made my a negative value there instead of a positive value, and I could have gotten all 4 transformations done. Now, that one's a little trickier, right? It captured a lot of behavior there. The last couple are going to be kind of tricky in the sense that they don't really give us a graph anymore, but they do describe some things. So one thing that you might find helpful here is to try and sketch the graph out for yourself. I'm going to draw just a really kind of quick and dirty example here. It's not perfect, but I just want to capture the most important elements of the graph here. So I've got a vertical asymptote at x equals -3, which I'll draw maybe as this like dashed vertical red line. I have a horizontal asymptote at y equals 0. Now, if the y coordinate is 0, that means I'm passing through the horizontal axis. So it looks like I haven't gone up or down at all. The graph also contains the points -2 comma 1. So maybe that guy, -2 comma 1, and also the point -4 comma -1, which is this guy there, -4 comma -1. The y-intercept of my graph is 0 comma a third. This is kind of a new one. When I say that I have a y-intercept, it's where I'm crossing the y-axis. So that's the coordinate 0 comma a third there, just barely above the origin. I'm trying to use that to figure out the equation, right? Now, I can get the horizontal and the vertical asymptote fairly quickly. I can find the domain and the range fairly quickly. My horizontal asymptote is y equals 0. My vertical asymptote is x equals -3. So there's no surprises here. It's more so when I'm writing the equation that there's something that's going to be a little bit different. What I know so far is that I have shifted left 3 units, but up or down none. So I could say y equals a x plus 3 to get it to shift left 3 units, and then I could write a +0 at the end or not write it at all because I haven't gone up or down. But I got to try and figure out the a term, right? There's maybe not just one way to do this, but the way that I'm going to focus on here is I'm going to use this extra information they provided where they give us a coordinate, a y-intercept in this case, of 0 comma a third. Now, a coordinate's always in xy notation. So if they say x is 0 and y equals a third, then I can say 1/3 equals a over 0 plus 3. And then what you'll notice here is we can actually solve for that a term to see if there's a vertical stretch or compression at play. Now, if I do 1/3 equals a over 3, and I wanted to try and figure out what that value of a is, well, just by kind of looking at it, some of you guys might recognize that the only thing that makes those fractions equal is 1. But another way is to multiply both sides by 3 to cancel that denominator, and you get the answer either way that way. So my final answer for this problem is going to be that the A term is just a 1, that there wasn't necessarily a vertical stretch in this case, which will on occasion occur. But the approach that I took there was I sort of substituted in the coordinate to get that guy. It's not necessarily the only way to do it, but it's one way. We'll do kind of this last guy, which is going to be similar. I'm going to start by sketching a pretty rough graph. Doesn't have to be perfect. And I'm going to just jot down my important information, right? There's a vertical asymptote at x equals 0. So it's passing through the y-axis. So I haven't gone left or right at all. It's got a horizontal asymptote at y equals 0, which is passing through the x-axis. So I haven't gone up or down at all. So my domain and my range is no different than the parent function for 1 over x. What you might notice on this one is that there's just this large number of coordinates that are given to us, right? It contains the points 1, 2, -1, -2, 2, 1, -2, -1, and also the coordinates 12, 4, and -12, -4, right? So we've got a lot of extra information at play here. A ton of extra coordinates that we're working with. And I actually think that's supposed to be -0.5, -4, and 1/2, 4. Yeah, I got another typo there that I should really fix there. There we go. Yeah, that makes a lot more sense. So in terms of trying to determine the equation, right, I know my template is like a over x minus h plus k. I haven't gone up or down at all, and I haven't gone left or right at all. So the last thing that I got to try and figure out is just the a term. You could do this a couple of ways. We know that we have a lot of coordinates we could plug into tests. So maybe we choose like a coordinate like 1/2 or 1, 2 and plug in x and y and solve for a that way. A different way that you could do it is to recognize that for our parent function, usually we have an anchor point at 1, 1 and at -1, -1. If you compare the coordinates, say 1, 2 with 1, 1, it's twice as tall as it's supposed to be. And if you compare the coordinates, say -1, -2 with -1, -1, it's twice as low as it's supposed to be. So that's maybe a different way to recognize that this a term is going to be -2. Now, let's say that you wanted to do the coordinate substitution approach. If I use this coordinate 1, 2, my y value is 2, and my x value is 1. And what I'll notice here is that that also tells me a equals 2 in this case, right? Yeah, a should be positive 2 there. There we go. So you get the same value there in either scenario. So if I wanted to write a final answer for my equation in this case, what I could say is that instead of 1 over x, it's twice as fast. It's 2 over x. And by taking a moment to sort of draw that sketch of that graph, it makes it a little easier to find my answer in that case. Yeah, I think that is the last one in our examples. As we start to wrap up for our time today, I think what I'll do for our next lesson is make these last couple of scenarios some warm-up problems. I want you to go ahead and try the reverse process. Try graphing the function when you're given the equation. We were sort of working the backwards process where you had the graph and we got the equation. This is just going to continue to reinforce that as you're working from equation to graph. I'll go over these when we come back for our next lesson, regardless of whether I'm back in class or not. If I'm stuck at home, I'll do a video recording of it. But then from there, I want you to go ahead and wrap up the notes and then start finishing up the practice for 6.1 and work through the practice for 6.2. As we get closer to the end of the lesson, make sure that from the sub, you get a copy of the practice for 6.2. Apart from that, though, I think that'll wrap it up for day 1 of our activity for 6.2 today. We'll take a second day to continue working through the notes and the practice here. Apart from that, I do miss being with you guys in the classroom. I really do hope I'm going to be back in the classroom soon. If I don't see you guys soon, I hope you have a great rest of your day, and I hope you have a great evening.